Hello, folks. Welcome to the NHS Genomic AI Network showcase 1 year on. We're delighted to have you all here attending, and we've got a brilliant panel of speakers who are going to showcase the excellent work we've done over the last year. We ask that if there's any questions, do put them in the Q&A section on the top, and feel free to peruse the questions that are already there and upvote your favorite ones so that we can prioritize what you as an audience want to know from our speakers. I'm Alex Deng. I am the director of the NHS Genomic AI Network, and here's what we're going to talk about today. We'll be starting off, is that moving properly for everyone? Super duper. We'll be starting off with me giving some thoughts and reflections over the last year and on the Genomic AI Network, moving to our guest of honor, Debbie Porter from the Genomic Transformation Unit. Our presenters from our various pilot work packages, including Dr. Antonio De Marveo, Sarah Ennis, Peter Fish, and Joe Zhang will be presenting as well. And we'll have special speakers in the form of Tony Thornburn from our Patient and Public Forum, as well as Dr. Tiago Martins from the MHRA with a special talk on how regulation will shape genomic AI adoption. The Genomic AI Network was now established in 2025 as part of several networks of excellence, and our purview is to accelerate the adoption of AI technology in genomic medicine to improve it. It's a collaboration led between the Southeast GMSA and Central and South. We have many collaborators in industry, arm's length bodies, education programs, academic institutions. It's a truly cross-disciplinary network. And I think it's a very timely organization to have come to life. If the Fit for the Future 10-year health plan for England is anything to go by, there's 119 mentions of genomics in this document. There's 60 mentions of AI in this document. And they are two of the 5 big bets on the future that the NHS is making. And by the choice of background they've chosen from the front cover of this document, suffice it to say that thematically, we think that we're aligned to what the future holds for the NHS. And the headline figure that I think is the elephant in the room here is that by 2035, this document has said we anticipate half of all healthcare interactions will be informed by genomic insights and other predictive analytics. And that reflects a big pain point that genomic medicine is going to have to address, in that the test demand to meet these half of all clinical interactions to be informed by genomic medicine or other predictive analytics is, with the current test capacity, going to be far exceeded. And that's going to be exacerbated by workforce shortfalls, both on the clinical and the laboratory side of things. And this is on a background of already patients who are, compared to other patient groups, more likely to have long diagnostic odysseys and possible missed opportunities for intervention by the very nature of genomic diseases often being rare and ultra rare. We know there's AI deployment happening, and there's AI deployment happening in the pilot studies that are happening under our umbrella, but they're often working in silos. And at the end of the day, Poppy, our program manager, will be discussing our direct efforts in de-siloing the work and making frameworks for broader adoption of these AI tools, and trying to defragment this technical and regulatory infrastructure that exists. You may recognize the 3-step plan of identify, evaluate, and scale if you follow the government strategy on AI. I'm pleased to say that we came to this independently before that document was published, but that sort of convergent thinking on horizon scanning, identification of best practice, making sure that it works in clinical pathways and scaling across the NHS is what we think a recipe for success. And this is how it maps onto specifically our functions as a team based in the Genomic Medicine Service Alliances of Southeast and Central and South. And we're not doing it alone, of course. There's NHS, government, academia, and industry stakeholders. The right kaleidoscope of logos are just some of our collaborators. We've had national focus groups, and I'm sure I recognize some of the names in the attendees today on the specific workflow needs within the highly specialized genomic medicine workforce, both laboratory and clinical. We're a world-first organization in having genomic AI implementation education in practical masterclasses for NHS staff. I'm afraid to say our November edition of this masterclass is booked up, but we'll be looking to have more in future, and you're welcome to join the waitlist in case of late dropouts. And we've partnered with organizations with large reach in this space, including AI with the Alan Turing Institute for ongoing genomic and AI webinar series. And of course, keeping the most important person in this conversation at the forefront is the patient and public forum, which we'll have a dedicated talk to in the first part of this session. Which leaves me the pleasure to introduce Debbie Porter, the Deputy Director at Genomics Unit, on how the future will unfold, and hopefully we'll gain some insights into what the world will look like in 2035 with respect to genomic medicine and perhaps AI. Thank you, Debbie.
Thanks, Alex. And it's a pleasure to be here today and hopefully provide a little bit of sort of national or centrally developed context for all of the great work that's going on inside the AI Network of Excellence. I wanted to focus today on preparing the digital infrastructure. So that's the title of the presentation. What the central team are doing to enable all of this great work to happen, and how we see the building blocks we're putting together, delivering essentially an effective infrastructure to utilize AI. Next slide, please. Thanks, Poppy. Okay, you've seen it already, and I think we're all excited about this ambition. It is a challenging ambition to have, but I think from all of the work that we've done, it is achievable. It's maybe a stretch target, but actually this is what we're trying to do, and AI is going to help us get there. So by 2035, those 50% of all healthcare episodes and interventions will be genomically informed. Considering we are at only about 870,000 tests a year, we're talking about billions of tests here. So it is a significant uplift. And the only way we're going to be doing that, because we're going the workforce to do it, is through utilizing technology and becoming much more efficient and productive. So I'm just going to highlight, this is the NHS England diagram, which shows what the aspirations are for our 10-year vision. And a data-enabled NHS is in that top right-hand corner, and currently in the left-hand corner at the bottom is the start point. So NHS England, NHS Digital, NHSX, HEE, all of those organisations merged on the back of also a huge set of waiting lists within COVID. That bridge to the data-enabled NHS is currently being built. Now, if you work around the top left-hand side of that bridge, you can see the NHS ecosystem, the partnership working that we're all trying to do, and then you see tech, and you can see genomics informing care as part of that build. A significant part of that build, and as Alex mentioned, 119 mentions in the 10-year plan, and a strand of DNA on the front cover. So it is absolutely in the broader NHS England perspective that genomics is going to be a significant part of that future. And genomics is right next door to harnessing new and emerging tech, including artificial intelligence. And those two things are joined together for a reason, because we are one of the largest data sets that the NHS is going to have, and we are building and accelerating at a rate of knots. So we have got a strong future together in the genomics, data and the AI space, and we want to enable this audience to accelerate along with us in terms of their knowledge and their comfort in using these tools as we move forward. Next slide, please. So here we are, fit for the future. What's in our plan? So technology, data and analytics, core enabler of the 10-year health plan. And you'll all be familiar with the fact that we are one of the three, the data shift is one of the core shifts from analog to digital. Alex also mentioned the 5 big bets. I'm going to focus on 2 of the big bets. The single patient record as part of a commitment to develop a unified genomic record. The single patient record will either be a record that the genomics unified genomic record fits into, that we feed as a single patient record, or it might be that actually, because the unified genomic record, which is the program that the genomics unit is working on right now, will be the pathfinder for the single patient record, because there's quite a lot of work been done on the architecture and the patterns and the modeling. So we may be able to, and we're definitely within the same portfolio of activity as the SPR right now. So that unified genomic record may be a pathfinder for, or at the very least, a feeder for the single patient record. And that is one of the big elements of the digital infrastructure that, that we have committed to. The other big element is the creation of the Health Data Research Service. So initially in partnership with Wellcome, and that was also covered in the Life Sciences Sector Plan, not just the 10-year health plan. That Health Data Research Service will be the research element of the learning continuum that we are all in right now. So genomics as an emerging science is going to be fed by research, and as more and more translational research is accelerating into our knowledge sphere, we need to use it in the clinical space, and then get the clinical data into that research space so that we can all accelerate around that, that learning system. And the commitment in the 10-year health plan was to expand and enhance the UK's consented health research data sets, develop the cutting edge infrastructure to deliver a comprehensive genomics ecosystem. And that genomics ecosystem includes all of the research elements. So we need to think comprehensively about how our data are used. It's not just about research. It's not just about clinical utility. It's not even about management information or service improvement or population health. It is a complete and utter ecosystem that is connected. And our unified genomic record will fit that ecosystem because it does feed all of those lenses. It looks through all of those lenses at the requirement for data. Next slide, please. So our single patient record, the commitment made by Wes Streeting was that we need to work together to create a single patient record owned by the patient, shared across the system so that every part of the NHS has a full picture of that patient. And we need to give patients visibility and control of their data. We need to provide a single version of the truth, the single patient record, and we need to enable the secure availability of that data for third-party applications such as research and clinical trials. So that single patient record is essentially the unified genomic record. We're already doing all of those 3 things in developing that record. Next slide, please. And the HDRS, the Health Data Research Service, will provide that single point of access through the single patient record, or to start with, the unified genomic record, uniting genomic data and clinical data at a population scale so that we can act as a magnet for global trials and AI investment. We need to put those data together in sufficient quantity and in sufficient standardized form to be able to train those AI tools on those data. not just the genomic data, but the matched clinical data as well. Removing the barriers to science and research by improving accessibility and that quality of data, whilst also maintaining the security. And we are committed to increasing the number of data-enabled research projects so that we can deliver on our ambitions to generate the AI world of the future for the NHS. Next slide, please. So I'm going to just go into a few deep dives into how we think we are going to enable this to happen. So interoperability between existing parts of the system is what we're trying to achieve here, so we can aggregate those data. Currently, we've got 189 secondary healthcare hospital trusts with electronic patient records, more than 6,400 primary care providers. Currently, there are 120 plus suppliers, 160 plus products, and 50 plus EPR integrators. So getting them all to talk the same language and communicate with each other so we can aggregate those data in the right size and shape is the real challenge here. And we've got EPR and LIMS providers, all of whom have built for their providers, for their users, what their users want. However, now we're looking at aggregating those data on a national basis. Being able to connect those EPRs and LIMS is what we're trying to do to support the use cases for direct care research, population health and management information. So the national programme is trying to deliver a global standardization and a series of genomic standards to accelerate those biomedical advances, which will enable us to share data and to interoperate between systems, both clinical data systems in the clinical infrastructure and across the research infrastructure. So we think that the global health services need to align on standards and generate a consistent set of priority requirements for industry to support, particularly in the EPR and the LIMS space. And we want to do that through a system of communication called FHIR, which is the Fast Health Interoperability Resource Standards. Next slide, please. And we are doing this, or connecting those bits of the system through 4 major projects initially, but this is about to expand. So digitizing the test directory is the first thing that we're doing. Currently, the test directory you'll be familiar with is a flat file Excel spreadsheet on an NHS web page. That is now just gone into private beta this time last week, with a number of clinical users and clinical scientists actually using the data inside it. It has got a new model. It is a new common data model. It is searchable. You can put terms into it, matching, fuzzy matching. So it is a clinical reference data set upon which the unified genomic record will be built. Order management is the event-based management system that will be used to provide real-time delivery, and again standardized through the use of FHIR and through a central core broker using other core systems such as the patient demographic services to signpost as a start the unified genomic record and actually identify the beginning of the of that data set that we need to build to enable AI in the future. Unified genomic record I've mentioned already. That's got the ability to connect not just the patient with their own clinical data and provide an insight for that patient, but also could connect other family members and enable cascade testing to happen. And again, all of it is underpinned by the delivery of common standards and a solid legal basis to do so. And there is a development of ministerial direction to allow order management to happen. And then potentially we will possibly move into legislation to allow the unified genomic record to happen and the single patient record to build on top of that. Next slide, please. This is the architecture for those architecture geeks amongst us. So the top left-hand box there in green is the Genomics digital genomics testing service, which is essentially the current test directory, but in a digitized version. And that acts as the reference data set and starts the standardization across all of this infrastructure that we're building. It uplifts the current test directory into a machine readable format. It's accessible through an API supported service. So it's automatable and a single point of truth for those systems who use those data. It provides the reference data set for the order management service, and I will go through that in a second. It will redefine and restructure the content of the National Genomics Test Directory on the basis of a much more usable common data model, and all based on, for cancer, for example, the WHO WHO Blue Books, and it will be much more familiar and searchable for those clinicians who are using it. Okay, I'm going to move on to the next slide, please. In the center and acting as the broker is the order management system. So it standardizes transactions, workflow, task management, and data storage. It will be accessible through either integration or interoperability, or if a digitally immature service wants to use it, through an order management portal. But ideally, we want it to be natively available in clinicians' EPRs. It will facilitate the standard messaging between organizational boundaries. It will bring organizations together and enable us to aggregate those data. It provides the data storage needed to support the movement, so you can track your request and your sample and basically say, where's my stuff? Go and ask the core broker. And it will interact eventually with the unified genomic record to persist order data sets. So patients and clinicians will be able to know what tests, what targets were available at the time that test was taken, and whether they need to review or whether it's still valid for subsequent longitudinal referrals, because this is a longitudinal record and those data will persist. Next slide, please. And then finally, the UGR, which is the ultimate goal of what we're trying to develop. As I mentioned, there are 4 lenses around which we can use. You can look at this unified genomic record. It will have something called purpose-based access control. So if somebody is a clinician on Monday and a researcher on Tuesday, the patient will know what their data was used for, whether it was for a referral, next referral onto the next layer of their treatment, or whether it was for their own consented research to do something with their data. It will provide that persistent data storage for order management. Currently, we are coming to the end of the alpha. We've had a proof of concept working with the NHS app and the National Care Record Service, and we've worked with Genomics England to actually demonstrate the use of a unified genomics record. It will feed MI platforms, clinical trial matching service, EHR and LIMS systems, and those data will be aggregated into a number of data stores that can be accessed for development of tooling in the future. Next slide, please. So here we are. This is what the structure of the new clinical and research infrastructure looks like. So through that single point of administration and access, the unified genomic record, there will be a federated object store, which will contain things like BAMs, CRAMs, VCFs, JSON files, etc., and PDFs for some people. It will be based on standards, so standards that are developed internationally. So these data sets may be shared on an international basis if patients agree to them doing that. Using something called GA4GH, which is the Global Alliance for Genomics and Healthcare, and they will be able to identify where patients' data are structured in a way that you can aggregate different parts of the genome if you need to look for a particular part of the gene sequence. I mentioned FHIR earlier, which was the messaging standard to connect those data. The UGR will be based on a single FHIR store. So every patient will have a FHIR record, which will contain a small amount of data, but not the large data sets in the federated object store. It will have when their diagnostic reports were undertaken, the document references, who the patient is, any connections to family members that they have approved and the family members have reciprocated and joined their data together, who the practitioner was, and their consent status for research. And all of this will be behind the NHS API platform, the APIM. And we've based the construction of this on a number of use cases, which you will see across the top there. The project is now in sprint 10 of its alpha phase. As I say, we should be just completing the alpha phase in October 25 and then moving into private beta. Next slide, please. So this is the this is the same representation as what you've just seen. So that federated object store. And what I wanted to do here was just to highlight the fact that that federation is between the number of genomics laboratory hubs, which are currently got siloed data sets, which could potentially be federated together, and Genomics England as well. That FHIR clinical data store is the FHIR server that you saw in the middle black box on the previous slide. Bulk query interfaces enabling data to be searched, genomic data to be searched, and also clinical data. And then the reference data store, which will be currently is being built on the federated data platform, which is the Genomics digital test directory. And then over and above that, on the right-hand side there, these compute services. So this is the next layer of development that we are doing now. And we are looking for a single bioinformatics workflow repository and compute infrastructure in the cloud. So those that piece of work is literally just being kicked off, but essentially these are the this is the working area within which the sandbox is being developed, where bioinformatics tooling can be developed, where AI can be developed, and that compute infrastructure can be then imposed on the data that's coming into the federated object stores on the left-hand side there. Next slide, please. So the ones that have been built and proven, federated object store, the clinical data store, and bulk query interface, that's what is being built now. The reference data set is now just gone into private beta, and then we're working on the bioinformatics in the next layer of development. Next slide, please. Everything is behind the NHS England API platform, and we are reusing all sorts of existing infrastructure where we possibly can. And the healthcare workers will be able to interface with this API platform, as will patients via the NHS app. And then NHS England will have back-end applications which will be working on the data, and other third-party providers will be able to access via the API platform with specific purpose involved through that purpose-based access control. Next slide, please. This is the data infrastructure that we are building. So the federation is between those 7 genomics laboratory hub regions, the geographies that you'll see in the colours on the left-hand side there, and then the 8th part of that federated data infrastructure is Genomics England's data infrastructure, because we're working on this together. We are developing a number of standards to upload into real time into the cloud. The whole thing is based on a cloud-based infrastructure, and we're working with J4GH to make that vendor neutral. So that infrastructure is not fixed with one particular vendor. So it's all going to be standards-based, including things like DRS write-back, FINA packets and pedigree standards. And then we'll be working with the Data for R&D program to undertake an IG review for SDE usage. So those data from the federated infrastructure can be fed into the HDRS in advance of the transition from Data for R&D into the new Health Data Research Service. Next slide, please. And I'm running out of time here, but I think probably I'm just about to wrap up. We're working with the NHS digital ecosystem, so the whole of the NHS. The Genomics is not just doing its own thing. We're part of a big portfolio of development, and as I mentioned earlier, the portfolio that we are in is the one with a single patient record. And we think that a single API platform and centralized identity and federation of those data as a truly unique opportunity to implement AI tools and provide data sets for training. We recognize that there are varying levels of digital maturity across the GMS, and we'll have to offer some centralized infrastructure and some more truly federated infrastructure as well. But that we are moving in the direction of travel where everything will be federated. And a key design aspiration is to be able to leverage the best public cloud and technology service while still supporting vendor neutrality through the adoption of standards such as GA40H standards. And so we're aiming to deliver a collaborative, federated, standards-driven compute and storage in the cloud to enable the development use of AI power tools, and all of that by 2028. And that's the end. Thank you.
Thank you, Debbie, for that peek behind the curtain of what's about to come. And it sounds like all of a sudden lots of things are coming to fruition in alpha and closed betas, and we look forward with anticipation as these projects continue and develop the capabilities at a national level. If anyone has any questions, we may have time to revisit them in the Q&A, so put them in the Q&A section. Otherwise, we will proceed bang on time to our next speaker, who will be Dr. Antonio De Marveo, who leads the work package on one of our AI pilots, identifying patients with inherited cardiac conditions using natural language processing. I'll hand over to you, Antonio. Thank you.
Thank you very much, Alex. Please let me know if you can't hear me or you can't see the slides. Thank you very much for the invite and for allowing us to present all the very work streams that we have been developing as part of the Genomic AI Network for the past year or so. So today I'll talk about identifying patients with inherited cardiac conditions using natural language processing and actually a few other bits and bobs of AI approaches. I'm a consultant cardiologist specializing in inherited cardiac conditions and also a senior lecturer at King's College London. So a few slides just with background, first starting with disclosures. Sadly, I have no industry disclosures to report, and this work is funded by the Genomic AI Network and some other funding bodies and charities. So inherited cardiac conditions, these are genetic diseases that affect the heart's rhythm, the heart muscle, the blood vessels. Because they're genetic in nature, they run in families. And they're particularly serious because the complications often affect young, otherwise healthy people, and often the first presentation is with some catastrophic event such as heart failure or sudden cardiac death. And individually, there's many of these conditions. Individually, they're relatively rare. So dilated cardiomyopathy, about 1 in 250 people affected, hypertrophic cardiomyopathy, about 1 in 400, and then rare syndromes like long QT or Marfan, even rarer than that. But together, collectively, they cause a major burden of disease. And early recognition really enables treatment, prevention, risk management, and importantly, family screening, so we can identify other asymptomatic carriers. And Debbie and Alex have already set a bit of the background, but we have lots and lots of data across the NHS, but it is really hard to integrate it all, to read it all, and to make the most use of it. So as it stands, these rare conditions, most patients are identified only when their symptoms develop. So we have the first contact with healthcare is actually with expensive, long admissions to hospital, intensive care, expensive treatments, rather than at the cheaper preventative end of things in early disease. And the rest of the iceberg is really information that is hidden. It is routinely acquired, so we're not asking for additional data, but we're just trying to find ways of interpreting that data better. One of the main challenges is that lots of patients have right tests in the wrong settings. They have an ECG at their general practitioner. They have some blood tests when they come to an outpatient appointment. They might have an ultrasound of the heart as part of preoperative assessment. But it's very difficult to have the staff, the experts, to integrate all this, to look at all the tests all of the time. And without doing that, without integrating all the information, lots of these early disease features are unrecognized. And then specific to genetic testing, we know that genetic testing, family screening, cascade testing are rarely offered outside specialist care. We are moving towards mainstreaming, but that is still not happening in practice. We don't know how many patients exist, where they are in their clinical paths, when they've last had tests, which tests they're missing. There are many barriers to genetic testing across the workforce, both systemic and individual. Still, despite lots of the education initiatives that have been carried out, most of our colleagues still don't know who to test, when, how. There are systemic biases in access. For example, we know patients from white European backgrounds are about 8 times more likely to access advanced care. So it is also difficult to kind of systematically identify patients across the health system that would meet criteria for specific clinical pathways, for treatments, for new studies, and for genomic testing. So what did we set out to do? Well, it was basically to tackle all of these barriers across the pathway of our patients. So we think AI can help us detect and monitor patient status by integrating unstructured data, so free text and structured NHS data, such as blood test results or parameters measured on imaging. We want AI to continuously read through this data so that information can be updated in real time. We want to automate time-consuming tasks that either are very resource-intensive, mainly specialists, healthcare providers' time, which either results in them being delayed or perhaps not done systematically. We wanted to develop tools that support the clinicians in decision-making, so prompts, decision support tools that assist them in making the referrals for genetic testing, do this correctly, so enriching the referral data to our genetics lab. By making it systematic or rules-based, we would hopefully reduce biases in referral. We want the system to increase efficiency, so all this is meant to be doing more with less. So we want to be more efficient. So get patients to one-stop genetic clinics, for example, so avoiding lots of complex clinical pathways. We want to highlight the patients that need early review, but also at the other side of the coin, we want to also identify patients that have had reassuring tests and they are asymptomatic and perhaps do not need to be seen as regularly. And finally, at the end, we wanted to be able to easily identify patients for clinical trials, emerging therapies, but also collect large-scale data sets that allow us to improve discovery, predictive modeling, outcome forecasting. And we wanted to do all of this in a flexible, vendor-neutral, low-cost, open-source architecture that could then be easily distributed across other NHS environments, both local trusts or national environments, as Debbie just described. So the technology we used for a lot of the work I'm about to present has been kind of packaged under CogStack. CogStack is a company that was funded and started by several NHS trusts like King's, gstt, and academic partners such as KCL and UCL universities. At its most simple and broadest use, it is a data lake. So it ingests all types of structured and unstructured data from electronic health records and all the systems from imaging, echo, ECG, all types of different data, it pulls it together. And once we have this data lake, we can apply different layers of AI for different tasks. So today I'll talk about natural language processing and also large language models. And using these two types of techniques, we can really translate and distill this messiness of the data into structured clinical terminologies, mainly SNOMED and HPO coding. So what does it look like? So you've all received letters or seen letters from secondary care to GPs, vice versa. I've seen reports of imaging or tests, so they're in free text that someone has typed out. What these approaches is allow us to read through text, perform named entity recognition, match it to a standard terminology, for example, SNOMED or HPO, so that we then have specific structured data. It also allows us to understand context, and this is very important. Just because a condition or a symptom is mentioned in the notes, it could easily mean that that diagnosis is being excluded, queried. We're talking about family. We're talking about a past or a possible future event. So understanding the context is really critical for this. So my team has really worked on the past years developing lots of models to identify several concepts associated with these rare conditions and also with associated comorbidities. And how do we know that the model is performing well? Well, all for each of the individual models that have been trained, we can produce a report on how good or bad it is. For example, I'll show you here 3 examples. We have a natural language processing model to identify hypertrophic cardiomyopathy, trained in over 7,000 documents, 11,000 annotations, and been externally validated. So we can see how good it is as identifying a family history or recognizing that the diagnosis is present in the patient, of using different metrics such as precision, recall, and then the combination F1 score. We can do the same with large language models as we ask the model to extract different features from clinical notes. Is this HCM? Is it apical? Is it sigmoidal? We can see for each of the features that we consider important to characterize the patient, how good each individual model is. And we've also trained several models to assess comorbidities or exclusion criteria. For example, dilated cardiomyopathy is a condition of the heart muscle that causes heart failure, in the exclusion of things like coronary artery disease, ischemic heart disease, myocardial infarction, bypass, and valve disease. And you can see here how good is the model at recognizing those other features and excluding them from the diagnosis. So we have we're not just identifying specific mention in the notes, but actually making sense of the whole corpus of the patient's data sets. We've been carrying out lots and lots of work also on the technical aspects of it. As we mentioned, we want to make these models as light as possible to be run in NHS infrastructure, which is very variable across each site and each hospital, each trust. So we systematically perform analysis, for example, looking at the size of the models, how big they are, how long they take to analyze each document, and at different complexities of the model, how good they are at performing the tasks, such as identifying patients or risk stratify them. And you see here one of the projects we're carrying out to identify HCM. We use several increasingly larger large language models, 1.5 billion to 70 billion. And you can see at the bottom here how long it takes per document. So 31 seconds per document, etc. And then we see how successful and how reliable each of these models are at extracting the data and doing the risk stratification. So what tools have we developed? Well, at the most basic end, we have a patient dashboard. So after we identify the patient cohorts, we can easily navigate through their data sets, see how many patients we have, their basic demographics, their weight, their height, their ethnicity, what medications they're taking, what other diseases are they being treated for, when was their last appointment, when they're coming back next. Then at the most exciting end, and we still have to improve on the display, but these are the working demonstrations of our applications, of our tools. So we're developing tools to identify these patients. So here, what we show you is a model that is live. It is reading through CT reports in this case, but it could be going through any other test. So the model is going through the CT report. It's trying to read and make sense of and summarizing the CT report and comparing it against the guidance for referral to the R125 thoracic aortic aneurysm genetic testing as per the National Genetic Testing Directory. So you can see how it is thinking and how is it making sense of it. Is identifying the patient's age, how big the aneurysm is, if there's comorbidities, and at the end will kind of prompt the clinician or suggest that the testing appears to be indicated based on whichever criteria we want from the genetic testing directory. In this case, aortic aneurysm or dissection with onset before the age of 50. And we have models like this for several inherited cardiac conditions. We also want to assist clinicians making genetic testing referrals to make them better and enrich their data with their referrals with as much useful information for the clinical genetics lab team. So the model I show you here is reading through clinic letters from patients. And then the model is summarizing all the information, identifying all the different comorbidities, phenotypic characteristics, risk characteristics, and at the end it produces this type of PDF document summarizing all the clinical notes for the patient. So it's a 53-year-old presenting with ventricular hypertrophy, types of apical hypertrophic cardiomyopathy, and all the other features. And importantly, adds in the HPO IDs, which are the language that the clinical genetics lab found more useful to match the genetics with the clinical phenotype. As part of the tool sets we've established, one of the things we have incorporated is a way to interact with the clinical notes. So our app allows all the documents for a given patient to be uploaded, and then for the clinician or the healthcare provider to interact with the notes. So for example, here we're asking, can you tell me when Tim was last discharged? Then then the model goes in and reads through the notes and presents an answer and shows the source of such answer. So he's thinking through the question and says, Tim was last discharged on October the 5th, and then it presents the discharge summaries that then the clinician could easily click through and be presented with a summary of the admission. What we do clinically right now in terms of risk stratifying patients is we have these online calculators. So they're actually on the web. So every time we see a patient to stratify or to predict their risk of a complication like sudden death or heart failure, we go online, and then we open a document at a time. So what is the patient's age? We open the echo report and put what's the maximum LV wall thickness. Then we read through our notes and figure out if the patient has a family history of sudden cardiac death or not. Then we open a Holter report, find out if they had an unsustained VT or not, look through symptoms, and eventually we have a risk score that we then basically transcribe to the clinical notes for the patient from the web. What we have now developed is a tool that using a large language model can go through all the patient's notes and go through sequentially over through all the variables that goes into this risk calculator. And we've done this for hundreds of risk calculators. We're just now validating one by one. Ask the model to fill with data from the notes. On the right-hand side, you had a possibility for the clinician to validate or edit in case there's an error. And at the end, the risk is automatically calculated, and you can interrogate how the model extracted the data, where from, which variables. So that's for an individual patient when he's in clinic with us. This tool also incorporates into a larger dashboard that is ingesting data live 24/7 from the electronic patient records and calculating this risk score automatically. So you can see here how a patient's trajectory as new tests come through, or there's an admission where the patient has fainted to A&E. All this different bits of data from different health systems is integrated, prompts risk score recalculation, and then presents this data to a clinician. The next step, which we're about to start, is can we improve on the current risk stratification tools? Can we do more with all this data? At present, all these risk calculators take 5, 10, 15 variables because those are the ones that are more regularly measured, because they're easier to input in a calculator. But actually, we're throwing away tons and tons of data that is collected throughout the patient's life course. So the next stage is really, can we use these large language model architectures and other forecast approaches to do more from all the existing data? So at the stage, where are we? We're testing, validating, implementing, and scaling up. So we are currently performing shadow mode deployment at both the gstt Trust and KCH. So running lots of these apps in the background, comparing with what clinicians are doing and documenting at new appointments. We're ongoing validation of each model and each comorbidity and every exclusion criteria by experts. We also started external validation at several other COGSAC NHS sites. COGSAC is present in 10 or 15 other sites on the NHS, and we're collaborating with colleagues there to deploy these models that are all going to be open source and easily to deploy locally. And we're actually doing one more step of validation, so really a pilot of bringing patients face-to-face to clinical genetics clinics or inherited cardiac conditions clinics to be seen by a clinician, and then be able to validate, were the diagnosis correct? Were these patients that are being identified for genetic testing correct? Do they meet the National Genomic Test Directive guidance? And then invite patients for interviews and focus groups to kind of debrief on their experiences. So I'll show you there just one of the 3 pilots we're doing. We kind of trained a model to identify patients with aortic dissection, read through tens of thousands of CT scan reports over the last 5 years in the trust. Whenever these aortic dissections were identified, we compared against lists of patients who have had genetic testing, and if they're not, we've invited them for clinic. And this pilot is now complete, and we're doing the current assessment of this pilot. This work was done by a very large team, and I would like to thank everyone both on the data science side and the clinical side that has contributed. Thank you very much.
Thank you, Antonio. Every time I see the work presented from your work package, it strikes me that the breadth and depth of work increases, and the sort of scope of utility for AI is expanding all the time. It's fantastic to see. Thank you so much. We do have a couple of questions, but we'll head to them if we have time at the end, if that's okay, just because we're running over. And I'm going to move on to what may be the highlight of certainly a lot of our audience's day on hearing the patient voice, and that's with a conversation with Tony Thornburn and Nikki Scott. Over to you two. Thanks very much.
Thanks, Alex. And I have the pleasure of interviewing Tony today. So, Tony, welcome to the stage. It's great to be here and to have you and give an opportunity to showcase the work that you've been doing to ensure people and patients have a voice as part of the network. To start us off, Tony, tell us a little bit about yourself.
Thanks, Nikki. Well, my name's Tony Thornburn. My daughter has a condition called Behçet's, which in some populations seems to have a genetic association. And this prompted me to get involved with the Genomic Medicine Service. I've had the privilege to co-chair with Dr. Anwar Halhak from King's College Hospital, the AI Public Perspectives Forum.
And so tell me a bit more about what the Public Perspectives Forum is and what it does.
The forum's made up of around 20 people from all over the country and walks of life. Together, our role is to actively ensure that people's voice and thoughts are heard and considered as we develop AI processes and tools within the Genomic Medicine Service.
Sounds great, Tony. So tell us all a bit more about what the group have been doing so far.
But firstly, we needed to hear from as many people as possible representing all communities. And we proactively visited and listened to people from all over the country and engaged in a conversation about how AI could or should benefit genomic medicine. We listened to their thoughts and captured their initial questions and concerns. And you can read everything they told us in our report, which will be posted later in the chat.
Thanks, Tony. And I was very lucky to have been in some of those conversations, so I know how useful and insightful they were.
Yeah, absolutely. I mean, you facilitated brilliantly, if I might say so, the initial 100 or so participants, and their feedback enable us to begin to understand what is important to people.
So from those conversations, Tony, I mean, I can remember them well, but you formed a smaller group, didn't you, that you've now been working with to shape the conversations going forward?
Yeah, that's right. 20 of us have met regularly, and we're most grateful to everyone who has committed time and energy to the forum. It's most important.
And on the screen now, we have some of the top themes that we heard during those conversations. Now, most of those won't be a surprise to the audience, Tony, but talk us through some of the more contentious ones.
Of course, most of us will be familiar with these headlines, but some of them are hard to overcome and subtleties lie within. For example, if something goes wrong with data storage and security, then people told us they want to know straight away. But that's no different to any other health data breach. Equally important was that the data should be anonymized so that no one can inadvertently track the data back to an individual. Conversely, when one is dealing with a specific patient, one needs to be able to identify them for diagnosis and care pathway purposes. And Debbie Porter reflected this in her talk, and specifically the unified genomic record.
So these are big issues, Tony, that don't have a simple fix, of course.
Yes, but on a positive note, everyone we've spoken to are supportive of AI being used in genomic medicine. They felt very positive that AI could speed up their care, offer the potential for early diagnosis, reduce human error, and eliminate even bias.
And the report makes a great read, and we'll post it in the chat so that everyone can see it. But in the report, I can see that you've raised the people you spoke to raised really valid concerns about how the NHS would have the capacity to offer both treatment and support if, of course, AI is identifying, helping more people to get a diagnosis. Exactly.
We've had fascinating discussions about the potential benefits and possible pitfalls of embracing AI within genomics. Regarding the last point you make on capacity, potentially I think it will make the whole system more efficient. The number of individuals that are quietly wandering around with an unknown condition or various comorbidity and spending much time within the NHS, seeing a myriad of clinicians, etc., is considerable. The whole triaging process will be much more cost effective and, more importantly, a better patient experience journey. And Debbie Porter mentioned the single patient record, UGR et al. Anwar raises the black box problem. That's a term used in science, computing and engineering. So a black box, aka your AI machine, is a system which can be viewed in terms of its inputs, outputs and transfer characteristics without any knowledge of its internal workings. So this taps into concerns related to trust and decision making, as well as the need for human involvement and oversight. However, the deeper issues that emerge from this patient focus group are not just about the use of AI as an intervention, but also a particular uncertainty regarding the influence AI intervention itself but rather on the influence of AI on the nature of their relationships, with healthcare professionals in discussing their health and healthcare decisions. And then this leads into patient decisions and responsibilities, trust in the face of AI, and the role and influence of AI in shifting and changing the nature of healthcare professionals, communication, and healthcare service. An overarching theme, embracing all topics on this slide, regards communication. Participants emphasised the importance of transparency and explainability in the use of AI. Accessible communication was viewed as essential to ensure patients understand how AI contributed to diagnostic reasoning and decision making. Making linked this to the empathy and the human connection in clinical encounters, and stressing that AI cannot replace the role of a human communication. Rather, clinicians must remain central in explaining results, contextualizing AI outputs, and ensuring that patients feel heard and understood. The consultation was thus positioned as the key space in which trust and transparency could be established.
Thanks, Tony. There's a lot in there, and I would encourage people to read the report if they could. But so going forward, Tony, what's next for the group?
Yes, well, from the report, obviously, there's quite a lot of work being done, and then the summary of that will be produced. So that first paper was all about immediate concerns. Our working priorities list will be refreshed at our next meeting, following consolidation that Anwar has been conducting. During a hybrid face-to-face and online meeting in Birmingham, we were fortunate to have Dr. Natalie Banner, Director of Ethics at Genomics England, and she talked with us, and what became readily apparent was that there has already been a good deal of discussion, analysis and so forth carried out on issues of concern to the general public, patients and participants, but not readily visible in related areas. An obvious example that cropped up was concern over medical insurance, for example. I've been pushing for a frequently asked question list, tabulating the topics that have been raised, need to be addressed, and annotate against those which have been sufficiently answered with reference, links and such forth, and those ones that have not. Those are the ones we need to channel our effort. This will benefit anyone joining new to the debate and save nugatory discussions which otherwise inevitably occur. We've also been awaiting output from the other work packages so that these can be formally exposed to our panel, some of which will be presented today and has been already. So following today's session, we will discuss the projects and presentations, including feedback from all those who have kindly joined online today, together with other research that Anwar is doing, whilst continuing to identify how best to hear from more voices. A myriad of organisations are engaging the public on the use of AI, but our continuing work with specific to AI and genomics is, I opine, vital for the future. You might not be able to put an immediate savings pound sign against some of it in the short term, but if our approach, NHS, DHSC, gets it wrong, it's going to cost downstream. Take up, errors, patient confidence, withdrawal of support, and so forth. There's more than enough suspicion of science within the community as it is. And it must also be accepted that everyone is not going to agree to everything all the time. So I suppose in summary, we're rightly proud of our approach, which has enabled a wide range of people to get their voices heard and to remain involved in the discussion. And this we aim to continue.
Thank you, Tony, and thank you. I know there are many of your group also on this session today, so we are very grateful for obviously all your time and commitment and energy and enthusiasm that you give to us, and we look forward to continue to work with you all. Thank you. Back to you, Alex.
Thank you, Nikki, and thank you, Tony. Enlightening and very distilled conversation on what's been a lot of work for a huge amount of people, many of whom have volunteered their own time for this. So we're very grateful to our patient and public forum for their continued engagement in helping us make this the best network we can that serves the need of you.
Thanks, Alex. And actually, I just flag up, for instance, that Antonio, with his project, obviously engaged with our group before he put materials out to do the work he's doing. So it was a classic example of this co-production.
Perfect. We have then 3 minutes and wherein I'll look through our Q&A section and try to put to people, if they're still on the call, Antonio and Debbie, on what the people are asking. Debbie, we have one here for you from Damien Smedley. For Deborah, fascinated to hear more about the bioinformatics workflow repo and how we can all get involved in testing, etc. Are there opportunities, or when will those open up for the broader bioinformatics community?
So the work that's going on at the moment is literally a quick and dirty pathfinder. So over the next 3 months or so, we are going to work with one of the cloud providers just to see what is in the art of the possible. If we've got 5 use cases at the moment, which we're still debating on which ones we are going to test. So if anybody's interested in putting forward a particular use case, whether it's collaborative working across GLHs, whether it's developing a bioinformatics tool, whatever it is at the moment, if you want to put a proposal forward, if you can either link me in or Wook is probably the best filter for the decision, then please do put a proposal forward.
Okay, it's all to play for, Damien, and it sounds like. And another one for you, Debbie. Natasha Spiridu says, thank you for the talk. Great to see all the progress made in the streams. Will access for research be on the basis of consent, or would anonymized data be accessible without necessarily requiring consent, to explicit patient consent, I assume?
If it's completely anonymized, I think we've not really considered that at the moment. What we're considering with the UGR is the data being consented by the patient. So the purpose of the whole project is to be able to re-identify data. So at some point, it's going to have to be completely de-identified and put into a completely new set of environments if we want to work differently. So I think the purpose of what we're trying to do is getting a patient to give consent, to be notified that there is a study that they could potentially be consented for if they want to be. So to give a very broad-based consent is difficult. But what we can do is to say, would you like to be contacted for a particular study, and would you like to be then consented for that study? So and the answer currently is completely de-identified data is not within the bounds of what we're trying to do, but is possible. What we're trying to do is consent people so that they know where their data have been used and for what purposes.
Thank you so much, Debbie. Antonio, I see you've been studiously working through your answers on the chat itself. So if you've asked a question of Antonio, there's a reply already in there, and there's interesting conversations on the sort of platforms you used and the way models are used clinically. With that, we have a 5-minute comfort break, and then we'll bring you back at 2:15 for part 2 of this Genomic AI Network showcase. See you in a shortly. Thank you. Welcome back, folks. Our next speaker is Dr. Tiago Martins, who's a devices regulatory specialist from the MHRA, and we're delighted to have him as a special speaker on the long view from the regulator's point of view on how AI adoption in genomic medicine may be shaped through this regulation. Over to you, Tiago. Thank you.
Thank you. So good afternoon, everyone. So I hope that you had a fast and refreshing break and that you are ready for the second half of this extraordinary summit organized by the Genomics and AI Network of Excellence. So well done to Poppy and Alex and all the team on bringing us all together. today. So my name is Tiago Martins, and I am a devices regulatory specialist within the innovative devices function at MHRA. And thank you very much for inviting me to share some of the work that the Medicines and Healthcare Products Regulatory Agency, so MHRA for short, is currently undertaking in the genomic field. Today, I will provide an overview of how regulations are shaping and supporting the adoption of artificial intelligence in genomics medicine and how regulation can act not only as a safeguard, but also as a strategic enabler for innovation. So I will also highlight some of the practical challenges and opportunities we are encountering as we move towards a more AI-enabled NHS. So in this short talk, I will guide you through some introductions and context to the promise of AI in genomic medicine, the current regulation landscape, some of the key regulatory challenges, some of the recent developments and opportunities, regulatory enablers for the genomic AI, and lastly, a few points on how we might focus looking ahead. So let's begin with some context. So the promise of AI in genomic medicine is immense, but so are the regulatory challenges. As AI becomes integral into diagnostics, data analysis, personalized treatment, regulatory frameworks must evolve and ensure safety, efficacy, and public trust. So my presentation today sits at the intersection of technology, ethics, and healthcare policy. Regulation is not just about setting boundaries, but is about enabling responsible innovation. So in the UK, we are seeing a real shift towards regulation as a driver for safe, effective, and equitable adoption of new technologies. The promise of AI in genomic medicine. AI offers a transformative potential in genomic medicine. So it enables faster and more accurate analysis of complex genomic data, supports personalized medicine, rare disease diagnostics, and pharmacogenomics. So within the NHS and Genomics Medicine Services, there is the capacity for piloting AI tools for variant interpretation, for clinical decision support, for multi-omics integration, and these applications can significantly improve patient outcomes and operational efficiency. So, for example, if an AI-driven variant interpretation can help clinicians identify rare genetic mutations, as we had heard earlier, more quickly, uh, leading to a faster diagnosis for patients with rare diseases. Similarly, if an AI-powered clinical decision support tools can help tailor treatments to individual patients, improving both efficacy and safety. However, integrating this AI into clinical workflows must be managed carefully to ensure that technology and technological advances do not compromise ethical standards and patient safety. So this is particularly important in genomics, where the stakes are high and the data is deeply personal, as we all know. So some key regulatory challenges. So there are several challenges must be addressed to enable safe and effective AI adoption in genomic medicine. So the first that actually has been mentioned by Tony before, the transparency and explainability. So clinicians must understand and trust AI output. So without explainability, adoption will stall. So for instance, if an AI tool suggests a particular diagnosis or treatment, clinicians need to know why. Bias and equity are another pair. So underrepresentation in training data sets can exacerbate health disparities. So if AI models are trained on data that doesn't reflect the diversity of the UK population, there is a real risk of perpetuating or even worsening existing inequalities. And also clinical governance. So adaptive algorithms raise questions about liability and oversight. For example, raising questions such as who is responsible if an AI tool makes a mistake, or how do we ensure ongoing oversight as algorithms evolve. So these challenges require coordinated policy responses and stakeholder engagement to ensure that these AI tools are both innovative and ethically sound. So it's not just about compliance, but it's about building systems that clinicians and patients can trust. My next slide will touch a bit on the recent developments and opportunities. So there is a strong momentum for AI regulation in healthcare, and the MHRA is part of the International Medical Devices Regulatory Forum and was the first country to join the Global Regulatory Network for Responsible AI in Health, gaining access to validated tools and early warning system, as well as leading on global standards harmonization. So the UK has launched as well a national commission on AI regulation to rewrite, so to speak, the rule book for the NHS adoption and bringing together clinical leaders, patient advocates, technical firms, and others so that we can push the adoption forward. Also, as I'm sure it was mentioned before, the NHS 10-year health plan mandates that at least 3% of the annual spend to be allocated in innovation. So definitely including AI on this bunch. So these initiatives aim to embed regulation as a catalyst for safe and effective AI integration, attracting investment and accelerating access to these transformative technologies. So, for example, at the agency, the AI Airlock pilot has provided a controlled environment for testing new AI tools, ensuring that they meet both technical and ethical standards before wider deployment. On the next slide, we can see the regulators enablers that we can see for genomic AI. So several regulatory enablers are facilitating AI adoption of in NHS genomic medicine. So, for instance, the human in the loop system, as most of our patient representatives have also raised, and as Tony's mentioned today, the AI Airlock pilot highlighted the importance of keeping clinicians involved in the decision making and ensuring that the AI supports rather than replaces human expertise. So the stakeholder collaboration, we at MHRA collaborate amongst a multiple number of entities, such as the Department of Health and Social Care, the National Institute of Health and Care, Excellence, the Department of Science, Innovation and Technology, the Information Commissioner's Office, Health Research Authority, and all of these are crucial to align regulatory, ethical, and operational requirements, as well as our close interactions with patient representatives, trade associations, and a close collaboration with the devolved administrations in UK. The next point would be the expanded data sharing. So including regulatory documentation in data sharing agreements can actually streamline approvals and enhance transparency for the genomic tools. So all these enablers show how regulation can support innovation while maintaining rigorous standards for patient safety and ethical compliance. By working together, we can create an environment where innovation thrives, but not at the expense of safety or trust. So for my last slide, I was just pointing a few topics for looking ahead. So looking forward, regulations must definitely evolve to support adaptive AI models, cross-trust validation of bioinformatic tools, and patient-centered safeguards. So the MHRA is committed to balancing innovation with safety, ensuring that AI adoption in a NHS or genomic medicine services is robust, equitable, and future-ready. So this includes refining regulatory definitions, enhance quality assurances, and foster international harmonization. By addressing these priorities, the UK can definitely lead in responsible AI integration, delivering better health outcomes and reinforcing public trust in emerging technologies, such as the ones we're talking about today. Our goal is to ensure that the benefits of AI and genomics are realized for all patients while minimizing risks and maintaining the highest ethical standards. So just to close, thank you very much for your attention and looking forward to take any questions that you can might have to take them offline and be supporting actually a witness on how we can collectively shape the future of AI in genomics medicine. Thank you.
Thank you very much, Tiago. If there's any questions, please do post them, as we have a couple of minutes to pick Tiago's brain for our next speaker. I have one. Tiago, there's several strands to the MHRA AI airlock going on, notably in discharge summaries, LLMs feature heavily. However, I don't see that there's a specific use case that uses genomic data yet as one of the airlocks. Where is that on the priority list for developing regulation and sort of piloting it?
So the AI airlock project, I believe it's run is just about to start the second phase of the project. So this is an open application point where anyone that has an AI powered tool that want to test and trial within the safeguards of the AI airlock project can apply for. So that is a limitation that we might not cover all the fields that there are out there because there is not application for a specific field coming through, or they may just not meet the required criteria that they set up at the beginning of the project. I do not know the specifics on that. But definitely genomics is one of the priorities, especially on how this is generating a wealth amount of personalized data, as well as the genomics field, I mean, and as well as these can definitely lead to patient healthcare improvements quite rapidly with all the new technologies that are coming through. So this is definitely on our list of priorities. There is a few guidances coming through and other things to come.
So it might be beholden to the practitioners of AI or developers of the tools to get in touch perhaps with the MHRA AI Airlock team if they wanted to see how a pilot might go.
Absolutely. I think
Okay.
the phase 2, I think, just closed. I'm not directly involved with that at the moment, but I believe that phase 2 just closed. They might be just selecting, but I'm sure there will be other chances to get involved. And I would advise everyone that has some tools that would like to test and check all the regulatory essentials, let's say, for a tool like this are within their scope, then just bring the tool over, and I'm sure the team is more than happy to assess it in a new application call.
Wonderful. If anyone on that call wants to have that conversation with MHRA, again, we'll be more than happy to lend our capacity, resources, and support to such an application.
Looking forward for it.
Thank you, Tiago. Very lucky to have you, and we are ready to move on to our next speaker. Our next speaker is Professor Sarah Ennis, who will talk to us about applying the algorithm or method of variant prioritization called GenePy for patient benefit in the genomic medicine pathway. Thank you, Sarah.
Thanks very much, Alex. Hoping you can see my slides.
Yes.
So, great. So I'm going to talk about a piece of software, an algorithm, if you like, for manipulating exactly what Alex was just talking about. It actually works directly on genomic data. And so there are some restrictions in its application so far, in that we need to use it behind the airlock in Genomics England or on patient consented data whereby the patients have consented for research. So I'll talk today about two particular applications, focusing on one of which is in Genomics England and the other is in a local high performance compute centre. But first of all, I'll talk about what exactly the GenePy project is and why we needed to bother with it. So the problem is that genomic data are vast, they're sparse, very, very sparse, and they're increasing. And so by that, I'm trying to explain what I mean by those three things: vast, sparse, and increasing, showing you here a picture of genomic data. And this is a depiction not of a whole genome or even a whole chromosome, it's just of one single gene. So this is the breast cancer BRCA1 gene on chromosome 17. Every dot you see, every one of these red dots you see on this picture represents a variant that has been observed in one or many individuals. On the y-axis, you can see here the frequency of the variant, or the minor allele frequency. So that's the frequency of the change compared to the human genome reference sequencing. And what we see here is that there are variants up here that are quite common. They have allele frequency of about 0.5, meaning half the people in the population have the alternative allele. And many people will be familiar with genome-wide association studies, which work down to allele frequencies of maybe 0.5, or some of the more recent genome-wide association studies might even have worked and analysed genomic data down to an allele frequency of just 1%. So that's this point here. So if you were to draw a line, a horizontal line across this grid here, only those variants with a higher frequency have actually been very well studied in association studies when looking at the relationship between variants and disease. The problem is, as we sequence more and more individuals, whether that be in the Genomic Medicine Service, in the All of Us project, in our Future Health, or in Genomics England, or in, of course, the NHS, we observe more and more and more variation all of the time. And you can see down here, as we go down to very, very, very low frequencies, and this y-axis is on the logarithmic scale, we see almost a solid line of variation, the frequency of variation across just this one gene. So in a gene that's about 80 kilobases long, we see about 34,000 variants, and only 661 of those are common. So the point is here, as we sequence more individuals, we observe more variation. Many of those variants are private to individuals or their families, and they're of uncertain significance. However, these very rare variants can have very large effect sizes, and in and of themselves, even though they may be very, very small variants, they can be sufficient to cause nasty disease. So we need new methods to analyze these variants. If we try and model these variants, we end up with incredibly sparse matrices that just get bigger and bigger and bigger as we sequence more people and observe more variation. The actual space becomes increasingly sparse because most people do not have most variants. Therefore, the data become less modelable, and they demand increasing resource to review and interpret. And so the GenePy algorithm is aiming to create one comparable quantitative score that reflects the pathogenic burden in any one individual. So not in a population, but in an individual, you can see how much variation they have in any one given gene. So it's a panel agnostic tool. It creates this score for all genes, for all individuals in that cohort. It reduces the dimensionality of these very sparse, rare variants, and it rescales genomic variant level data to the gene level. So instead of having one individual having 37 variants in any one gene, they now have one quantitative score reflecting their pathogenic burden in that gene. And so very briefly, it looks at each individual one at a time. It looks at every gene for that individual. It identifies what are the variants called in this individual for gene A, for example. It takes 3 measures: a score of deleteriousness for each variant, the allele frequency for each variant, and the zygosity observed in that individual. So do they inherit one of those variants from one parent, or do they inherit the same alternative variant from both parents? And it uses the GenePy algorithm to increase the weight of very rare and very nasty variants, and it creates a score for each variant that can be added across the gene, so that you end up with a score for each individual for each gene. And the idea is that you then are able to use these scores as a fast, scalable method for first-pass diagnostics that is disease and gene panel agnostic, and enable faster diagnoses or new diagnoses for patients. So when you generate the GenePy or run the GenePy algorithm, you end up creating a 2-dimensional matrix whereby every gene in the genome, you have created a score for each individual in your cohort. So for example, in the Genomic Medicine Service, you would have 1 row for each patient that has been referred for genomic diagnostics. And of course, the human genome has about 20,000 genes in it. So we have a limit to the number of columns in the matrix. But because this is a quantitative score, it's then possible to take any given gene, for example, a gene that causes epilepsy, and rank all the individuals who have within that cohort for their scores within that gene. And then you go from a genotype to phenotype approach. So you identify of the individuals who are very highly ranked for this gene, do they have a phenotype consistent with this gene, for example, epilepsy? And I'll show that working in a couple of slides' time. So initially we ran a pilot project in Genomics England applying GenePy, even though we developed this tool for looking at individuals with probably more complex genetics. We ran a pilot showcase in Genomics England, and we identified over 100 misdiagnoses, and were able to return these diagnoses through the Diagnostic Discovery Group at Genomics England. And so this work package within the Genomic AI Network of Excellence was to apply this GenePy algorithm at scale within the Genomics England project. And two of the postdocs in my group, Guo and Iman, were instrumental in making this work in the Genomics England environment. I'm not going to go into a huge amount of detail, but we have actually updated the GenePy software to allow it to incorporate multi-allelic variants. We've modified the workflow. It takes into account some study-specific attributes with respect to allele calling. We've modularized the workflow using Docker, and we've controlled it all using a Nextflow pipeline. And we've implemented this in the cloud environment called LifeBit that sits within the Genomics England infrastructure. We've tested and validated the GenePy pipeline and now implemented it across all chromosomes. And so now we have generated, just last week, finished generating the matrix for the entire aggregate 2 data set of 78,000 individuals. And we're in the process of now transferring that matrix from the LifeBit environment back into the Genomics England research environment. And we've also applied it in a more local cohort of individuals, not with a rare disease, but with a complex disease. And this is showing possible pathways of implementing genomics to patients beyond rare disease and integrating the rich clinical genomic data that Debbie was talking about earlier on. But first of all, talking about the GenePy data in GEL, we have to access the joint call VCF file on the aggregate 2. So these are all the probands and all the parents and all the germline genomes of cancer patients that were referred in the 100,000 Genomes Project. We have actually been promised early access to aggregate 3 data, which are due to come out either towards the end of this year or at the very start of 2026. So we've made the entire GenePy in GEL workflow available and free to access in the GitHub environment, but we've ported both of those things, the large 78,000 joint call VCF file and the GenePy workflow and all its dependables. That has been ported into the Genomics England LifeBit environment and executed on these 78,000. As I say, that has just finished last week, but of course we need to do sense checks on the data. So we have just pulled across some of a very small amount of data on some of the smaller chromosomes back into the Genomics England environment, research environment, back to where the clinical data are. So we compute the matrix in the high performance compute environment, LifeBit environment, but then once the matrix is created, we bring it back to where the clinical data, and that's what we're waiting for. Our colleagues in the LifeBit environment are facilitating this transfer of these large data sets back into the Genomics England research environment. But we've taken a sense check just to make sure that the matrices are making sense in the patients we've run these data on so far. So we've gone through some individuals who have already received a positive diagnostic report from the Genomics England project. And we've simply asked, if we rank the genes for which those individuals have a diagnostic report, if they have a causal diagnosis in gene A, we're just asking, is the GenePy score for that individual, for gene A, is it highly ranked? So we've taken out, undertaken that sense check data analysis, and we've extended that a little bit further to look at other individuals who have a negative diagnostic report. And this is the real value of GenePy in GEL. So about 75% of patients and probands referred into Genomics England do not yet have a genetic diagnosis. And this is where we wish to implement GenePy. And what we've done is for just those little bit of data we've taken back into the research environment so far, we've identified there are some individuals who we correctly identify have a high score in the SCO2 gene as causing pediatric motor neuron disease, and those individuals have already received a diagnostic report from a genomic medicine service and Genomics England. But we also looked at individuals who have even higher scores or were ranked above those people with positive diagnostic reports. And we looked to see if they had a similar clinical phenotype. So again, they're ranked highly for this gene. Do they have the phenotype? And even with just these sense checks, so this is not the systematic analysis we're planning when all the data are moved back into the Genomics England environment, but we identified these two siblings who have a normalized specific disease. So that's the high-level diagnostic referral reason for this pedigree was pediatric motor neuron disease. And these individuals, these two siblings, were actually ranked first for this gene. And we're able to go back and identify, of course, well, they're ranked first for this gene. It causes pediatric neuron disease. And we see, yes, in fact, these individuals have pediatric neuron disease. So we're now already, even just at the quality control checking stage, starting to filter these or send through these diagnoses back through to the diagnostic discovery group. And of course, this is again panel and disease agnostic. So where this was one example with the SCO2 gene, we had another example with the CRYBB2 gene, where we identified this family, where the individuals were ranked third highest amongst the 78,000 scores we observed for the CRYBB2 gene. These individuals were ranked jointly third, and these individuals were made up of father and 4 children, all diagnosed with severe early onset cataracts, and this gene causes cataracts. So again, it's another positive diagnostic report meeting Tier 1 diagnostic requirements to be returned through diagnostic discovery group. And then, of course, intellectual disability is one of the most common referral reasons for individuals. We had 2 families who were ranked joint top for the THOX6 gene, and these variants also meet Tier 1 diagnoses for this family. And the USP7, another individual, again, this was just one single, only the maternal data were available, but we were able to identify this diagnostic cause for this individual. So it's very early days, but just at the point of doing these sense checks, we're able to identify these 10 previously unidentified diagnoses across these 5 families. And we're hoping once we get the data back into the Genomics England research environment and are able to reunite the GenePy matrix with the clinical data for the whole genomic data set, that many more diagnoses will be made, and we'll be able to realize the benefit of GenePy in uplifting diagnoses. Just to show the potential benefit, looking at the clinical pathway for common or more complex disease, we have a local study looking at inflammatory bowel disease. And the benefit of this is that we're able to actually access the live clinical data now in a manner that we may soon be able to on the clinical genomics platform and the unified genomic record. So we're able to access laboratory results, prescribing data, move these data, de-identify them and move them into a relational database and then into a local secure cloud. Interestingly, we're also able to take unstructured data reports for these individuals, and at the same time we undertake genomic sequencing, and that's for the purposes of research. But when we take these individuals' unstructured reports from their imaging and radiology, so inflammatory bowel disease patients tend to have lots of imaging and radiology biopsies conducted at point of diagnosis. For 1,500 individuals, we actually have about 32,000 of these reports. And of course, it's not possible to get a clinical curation team to look at more than a handful of those. So we've developed a large language model and refined it for the extraction of structured data from these inflammatory bowel disease patient imaging and histopathology records. And we've just had this large language model published in Med last week. So basically, it goes through the raw unstructured reports, it generates and extracts key statements, and it turns those key statements into these standardized terms, be the ICD-10 codes, Uberon codes for anatomical location, SNOMED terms, or HPO terms. And here's an example where we're now fusing the GenePy score along with these digitally extracted HPO terms. So this is one individual, a proband. We've created their GenePy matrix amongst 1,500 other individuals with inflammatory bowel disease, and we've plotted the scores for all genes for this individual. So where they have a high score on the y-axis, it means they have a very high burden of mutation in that gene. Independently, we've extracted their unstructured clinical data and used the large language model to create the HPO terms. So for this individual, we have about 50 unique HPO terms. And then we take that list that we extract for this individual and cross-reference against the HPO terms assigned to all known genes. And we plot that on the x-axis, such that what we see on the x-axis, when you have a high score on the x-axis, it means your HPO terms overlap with these genes. So for example, the HPO terms in this individual largely overlapped with what one might expect to see in the STAT8, STAT3 or CARD8 genes. But of course, what's really important is when the HPO terms overlap for a gene in which the individual has a very high pathogenic burden. So this top right-hand corner. So this was a patient who was diagnosed aged 11 with Crohn's disease, but they have a high burden of mutation in the CTLA4 gene, and their HPO terms overlap with those expected for individuals with a CTLA4 deficiency. So this individual, we were able to have the genetic variants confirmed in the Salisbury Genomic Medicine Service LGL lab. We were able to have the variants functionally tested in the Great Ormond Street lab, and the patient's diagnosis has actually changed from a common complex disease of Crohn's disease to a pediatric or a primary immunodeficiency of CTLA4 deficiency. And of course, the important thing here is that this is a personalized diagnosis. There is actually a targeted drug, a precision drug, which this patient has now been referred for, and this drug, abatacept, is curative for individuals with CTLA4 deficiency. So again, just showing the value of integrating these algorithms with the sort of data we can pull from these clinical genomic platforms. So at that point, I'm out of time, so I'll just finish up by, of course, thanking all the patients that have consented for their data to be used in these analyses, the Genomic AI Network and the GMSA, and of course, our partners at Genomics England.
Thank you so much, Sarah. A really fascinating presentation on your technology, which really hits one of the big pain points in terms of yield and possibly time spent per analysis for getting to the end of that diagnostic odyssey for patients with rare disease. We'll step through. I don't think we have time for questions on this one, but if you pop them in the chat, perhaps Sarah, if you might look in the Q&A section and see if any are ready for your attention. We'll go straight to our next presentation for our penultimate pilot program of AI technology, which is with Dr. Peter Fish of Mendelian. Thanks very much, Peter.
Thanks very much. Poppy, can you help me find my presentation in the list?
Yes, I can. Give me 1 second.
Thank you, Sarah, for that. It's very useful because a fair deal of what I'm going to show today is actually on inflammatory bowel disease and monogenic inflammatory bowel disease. So you give me a good introduction on that piece. So quickly, as a company, we are a London-based company focused on trying to shorten the diagnostic odyssey of rare disease patients and get them to treatment and management as quickly as possible. Overarching, and actually the background behind this, we have a small team, mostly London-based, as I mentioned, clinicians, data scientists, and software engineers. And we take an approach looking at the entire patient pathway, and our aim is to move these patients through that as quickly as possible, from really lifting up clinical suspicion at the right time in the right place, all the way through down to the management. And actually, if we dig into this, there's a correct pathway for these particular patients, and there's a yes, Poppy. Sorry, you popping up your hand for me?
Sorry, I think you have to take control of the slides again.
Perfect.
There you go.
Thank you. Then. So yeah, there's a correct pathway for these patients, and there's a pathway where these patients end up with misdiagnoses or in bottlenecks or just in the wrong place generally. And ultimately, can we set up algorithms to move these patients from the wrong part to the correct part? And actually looking at the example that Sarah was running through, Sarah's working down in this analysis aspect. These patients are actually getting genetic testing, but it's the analysis and then reporting those variants in the right way at the right time. We work across all these levels, but in the GAIN project, most of our work is actually at this clinical suspicion point and really trying to find these patients at large. So in the MIBD example, Sarah Ennis is talking about patients who have had genetic testing, floating those with the right diagnosis to the top or floating the diagnosis to the top. But we're looking at patients who have inflammatory bowel disease diagnoses, but have never really been evaluated for monogenic drivers of that particular disease. Just an example of one of the diseases we work with, PNH. These patients present fairly early with blood clots in strange places into very significant emergency care. They often are managed acutely, but then may be discharged back into the community without further investigation. And actually, ultimately, you may be able to find these patients much earlier and pull them down the right pathway and get them onto the right management. So we have a technology called Mendelscan. It's a class 1 medical device under the old regulation, and it's an asynchronous scanning platform that looks across different diseases to float these patients to the surface. Ultimately, it integrates into electronic records. Clinicians then apply the technology to look through those records and identify these patients. We show a case report for these particular cases. Those cases are then reviewed by the clinician, and this is where Tiago said the word human in the loop. This is where the human comes in. And a number of those patients are selected for outreach, and they recontact those patients, and they offer those patients referral and testing where appropriate. We then generate in the background all of the aggregated data to support further health system change with those particular pathways. This is just a quick look of this, what it looks like. You can, clinicians be able to log in to the platform, have a look at all the patients that come up across their different practices or different disease areas, and then dig into the reports. The reports show the disease, some patient information, why the patient has been flagged, the NHS resources for that, and the next page of that report will show you what the appropriate next steps are for that patient if the clinician decides to take the patient further down that road. To date, we have applied technology, or at least our technology has been used by clinicians to look through about 10.5 million patients within the NHS. We have algorithms that cover around 750 different diseases. Not all of these have been deployed into practice yet, and definitely not all of these on the 10 million. To date, about 1,500 patients have been picked up and moved forward for the next step of evaluation. Around 30% of those move forward for the next step of evaluation. So within the Genomic Network of Excellence, our work package has a number of components. First component was the completion of the NHS AI Award project, which I'll give you a bit of information on. But importantly, I did do a presentation on this a few weeks ago as part of GAIN within the Alan Turing aspect that will be available for anyone to have a look at. There's a recording of this that you can go into all of the details to evaluate that. Secondly, and I've just joined these two together, we have an expansion component, which is to look at expanding the use of the technology into further primary care practices and networks, and additionally into alternative data access points into much larger data access points. And then we have an aspect focused on a new approach to this, which is looking across disease areas specifically, or at least phenotype areas specifically. So this is the inflammatory bowel disease component. We have an epilepsy project as well, and we have an inherited retinal disease. And in this case, I'm going to dig into a much more detailed inflammatory bowel disease example to give you an idea of how we're doing on that component. Additionally, we have an oncology piece, mostly looking at the cancer predisposition syndromes, which in some cases have a clinical manifestation prior to developing cancer. So an example would be P10 hamartoma tumor syndrome. Patients have a clinical picture that can be picked up way in advance of the cancers developing, although the cancers do develop quite early in these patients. So to give you a quick summary of the AI award, just to get that piece tidied up, This award was granted as the last round of the awards were taking place within the NHS in 2023, and we ended up with a phase 3 award, which is the first real-world deployment of the technology, but additionally generating a whole array of evidence around that. This award was brought in to the tail end of this award was brought into the GAIN network, and largely to allow support for that award within the network, but dissemination of the information within the network as early as possible. So just to give you an idea, this covered a substantial amount of different areas. We did a retrospective validation. We did some implementation aspects, including a public sentiment survey, patient acceptability, clinical acceptability, and a health resource modeling component, and deployment over 725,000 patients. The ultimate outcome was that the award took the Mendelscan technology much further down the NICE evidence framework for digital tools, which is very, very useful. Additionally, many of the disease algorithms were seen to be performing very highly, and it was suggested that these algorithms would merit further nationwide adoption. And lastly, outcome was that if future algorithms were developed within the same level of performance, these would also merit further adoption. So moving off that onto the focus on phenotype-driven algorithms that we've been developing, and one, as I mentioned, I focused down onto monogenic inflammatory bowel disease. This is a disease that, or at least inflammatory bowel disease, is classically thought of as this complex disease, but as Sarah Ennis introduced, a number of these patients will have individual or single gene drivers of this disease. And actually, if you diagnose with one of these single gene drivers, a monogenic driver, your management of inflammatory bowel disease is substantially different, which Sarah Ennis also mentioned on that particular case. And if we look across, or at least within the genomic testing directory, you'll see that there's a panel and actually a criteria for which patients should get tested. And ultimately, when you have an inflammatory bowel disease that develops early in life, and they take a cutoff at 6 years of age, the research shows that around 3% of pediatric patients with inflammatory bowel disease likely have a monogenic inflammatory bowel disease driver. The research does show quite a varied number of different prevalences in this. But if you get very early onset under the age of 2, that percentage actually may even rise to as much as 8% of the patients have these monogenic drivers. But ultimately, if you take this testing criteria that stands within the testing directory and apply this across the entire nation, you end up with far too many patients to test in the short term, at least, to try and make a difference. So ultimately, we decided that we need to dig a fair deal deeper, and we looked at the UK consensus guideline, which really lists a number of other linked and associated symptoms that might further increase the evidence that there's an underlying undiagnosed driver. We codified that and put this into the algorithm, and then linked up with the team at Oxford, Prof. Holm Ulrich and James Charlesworth, to really build this out and increase some of the data and weighting that we were doing within this algorithm. With that team, we identified that there's 2 issues within the population, inflammatory bowel disease population and monogenic population. The first one is, as we shown, these patients with inflammatory bowel disease often aren't pushed forward for testing because no one is suspecting a potential underlying undiagnosed driver. But additionally, there are a number of patients with inflammatory bowel disease that have been previously diagnosed, but they have an existing diagnosis of a monogenic disease, but no one has linked the 2 together to say, in fact, their IBD should be managed by a specialist team as well. So that together, we built an algorithm that allows us to integrate into electronic records, find patients and filter patients with inflammatory bowel disease diagnosis. The first cohort is generated where there's a patient with an existing rare disease and associated rare disease diagnosis, and that's pushed off to the side for further review. And then beyond that, patients get a scoring logic applied, which then defines that second cohort. So we took that algorithm and we put it into a validation study within the OPCRD datasets, and that's around 28 million de-identified patient records. And the outcome was we found 190,000 patients with IBD. Of those, 100 patients had an associated rare disease diagnosis. But beyond that, and another 500 patients were flagged up that breached the threshold within the scoring matrix of around 5, which is arbitrary. But ultimately, this is around 20 patients per million patients that we scan. So quite a manageable amount of patients to actively and manually review. But beyond that, then we took around 70 of these patients, at least from the group of 500, and we passed these over in a researcher de-identified format to be reviewed by Holm Ulloch's team, which they found around 80 to 90% of these patients showed clear indications of MIBD and warranted further evaluation. Ultimately, 5 patients were selected by the MIBD multidisciplinary team as patients who most likely had undiagnosed inflammatory bowel disease, monogenic inflammatory bowel disease. Sadly, this is a research data set, and these patients couldn't be recontacted. So those patients are still at large within the population. And that's a good segue into the next phase of the presentation, at least, which is the focus on the deployment aspect within the GAIN network. And within GAIN, the idea is that a number of algorithms, additionally beyond the MIBD algorithm, will be deployed into clinical practice. And the idea would be to expand that footprint across the different practices, or at least the different access points into primary care specifically. So we have a particular focus on expanding into primary care practices themselves and the networks. This is a time-consuming approach, as of course you have a number of GP practices that you need to try and educate and communicate and deal with on the administrative level, but it is directly to the canonical data controller. So we do engage in this, and we have got some practices stepping forward, but ultimately to find the needles in these haystacks, we need much, much larger haystacks. So as a second point in this, we've looked at these aggregated data sets. We've done some exploration directly with the primary care EHR software providers. A bit of a blocker on that piece is there's an expectation for substantial cash flow to unlock these particular projects. Beyond that, we've integrated or at least discussed in many instances with the ICBs and ICSs, and ultimately landing on the SDEs as a route to bring this type of technology into the NHS at scale. And of course, these SDEs were initially set up for research purposes, and actually, as Debbie Porter mentioned earlier, very swiftly we need to move these into actual clinical direct care situations to make an impact on the patients. And these SDEs do have a remit to deliver population health projects, which Mendelscan can be used in these examples. So we've worked closely with the Wessex SDE over the last probably most of this year to try and start setting this up. Wessex SDE is maturing and establishing itself as a builder SDE. So they create the platform and the backbone to bring the NHS data in and distribute that, or at least be used within their platform for various projects. And they've partnered with Kent, Medway and Sussex SDE, which will bring their primary care data in. And that'll be the first primary care data that lands in that SDE. There are about 3 million patients worth of data that'll be coming in there. So we've been meeting them almost weekly for the last 10 months or so to try and facilitate and set up this process. It's been a lengthy process, but a lot of hoops to jump through and a lot of different groups to gather sign-off from, both within Wessex and Kent, Medway and Sussex. And we are still navigating that at the moment. And we're hoping to really unlock a large-scale access route into the NHS via this. Some complexity exists around how you re-identify these patients, recontact the GP practices, and pass that information back down through that. Plus, the clinical team that's driving this sits within the genomic network, but ultimately a fair deal of action needs to happen at the primary care level. So how do we facilitate that? And these are some of the complexities we're navigating at the moment. So that's me. I'll stop there and hand over for questions.
Thank you, Peter. I will go through any questions that have come up for you. There's a couple of questions for Sarah, which I see you've addressed. If you do have any for Peter, please ask away. Peter, I have one. For the AI award, you weren't the only recipient. How did your product do out of the cohort that you were assigned, and do you see anything different that led to differential performance in generating evidence within the NHS based on what those or you know the structure or goals or the ways the products are managed?
Alex, great question. I can't tell you. I have no visibility on how the other products performed, and I've seen no press releases from those other products. There were 7 in total at that time. I can tell you that for us, there were multiple areas where we had to generate evidence, and some of those were far easier than others. We have a challenge in this space where our technology is a case finding technology. So it's definitely not a diagnostic technology. We're floating patients to the surface. So ultimately, our direct level of evidence is when we float a patient to the surface, does the clinical user find those patients valuable? So we get that information back very quickly, but in fact, we often get evaluated as what happens with those patients downstream. And that may take many years in case if there's a bottleneck in some of the diagnostic testing. So that's been a significant challenge that we've had to try and deal with in many different ways. Additionally, looking at the health economic benefit of technology like this is incredibly difficult because you have so many different diseases that the impact of early diagnosis in those diseases is very, very tricky to try and quantify in any usable format. So we try and aggregate that as much as possible and create models that can be used over and over again in different settings.
Thank you. If there's any further questions, I'm sorry for hogging you, Peter. If there's any further questions, please put them in the chat, and I'm sure Peter might have some time later to peek at them and send some answers your way. Thank you, Peter. And we'll move on to the last but no means least of our pilot AI projects, and that's with Dr. Joe Zhang and Martin Chapman from the London AI Centre team talking about their tool GenoLlama for automated genomic biomarker annotation. Over to you, chaps. Thank you.
Thanks so much, Alex. It's just me, I'm afraid, just Martin Chapman. Joe sends his apologies. Poppy and Co, are you happy for me to share my screen with my slides?
Yes, please.
Wonderful, I will do that. Make sure I get the screen. So hopefully you can see this. If not, give me a shout. Wonderful, thank you. Yeah, so thank you very much for the introduction, Alex and team. So as has been said, I'm going to chat a little bit about a tool that we've built or are in the process of building called GenoLlama. Possibly nothing new based on some of the presentations that I've seen in terms of the methodology here. As I'll talk about and show, what we're effectively doing is taking genomics notes, lab test results, standardizing them to a schema, again, as we've seen, at least in one of the other presentations, and then looking at the various downstream activities that we can support with this approach, one of which is clinical trial recruitment. So again, I'm aware, at least like I say from one of the presentations, that lots of other people are doing this, but I'll tell you a little bit about our particular methodology for doing this, and then maybe there's something of interest in there. So I'll just flash this slide up briefly. No need to go into the kind of, or worry about the details of the text here, just to kind of give you a very quick background of who we are at the AI Centre. So as has been said, we are the AI Centre. We sit within GSTT. And to all intents and purposes, we're a group of people who are passionate about AI. Many of us are doctors who have turned into software engineers. I'm sort of the opposite. I've always been a software engineer, but have recently, within the last 10 years or so perhaps not so recently, turned my hand to more clinical use cases. So what we do is as with this project, we offer, again, for want of a better word, AI services, building platform and infrastructure support to support AI projects, both within our trust, across the NHS and externally as well. So GenoLlama is one of these projects, and it's something that we're very excited about and very happy to be involved with. So drilling down a little bit more into the team itself, and what I'm going to sort of jokingly call my cop-out slide is the structure of the GenoLlama team so far. So as you'll see from this slide, I'm actually very, very new to the project. So I actually only started working on it a few months ago. So what I'll be doing today is really representing the great work that's been undertaken by my 3 other colleagues here. So Sigal Hajili, Joe Zhang, who we talked about already, and Sophie Ratkai as well. So Sophie particularly has got a genomics background, and as you'll see, we've kind of structured the project work to capture her great knowledge so far in the project, and then taking the project now forward through to completion, I will sort of bring the kind of computer science side of things. So this is how we've been working from the project start, and then in summer I took over. So much of what I'll be representing today is the great work of Sophie and team. So what did we start off doing originally? So this is WP3A. Our goal was the development of an automated AI-driven pipeline to extract existing genomic biomarker data in the EHR, which would unleash the potential this holds for clinical care and research. And then we want to link all this in then with existing pipelines. So it's fair to say that our focus has evolved a little bit, and this is mostly because of a kind of sibling piece of software we've been developing called GenoLlama. I should note that all the references to llamas are, as you might have heard, or as you might know, because the large language model developed by Meta is called Llama, so that's hence all these names. What GenoLlama aims to do, and again, as you've seen in some of the other presentations today, is to take unstructured text, in this use case, oncology notes, translate them into a structured schema. And then again, as you can see here from the right, once we have that schema, then we can enable various downstream tasks. We've actually found quite good accuracy on this. The team have actually found greater than 98.5% accuracy on this based on the sort of methodology that I'll explain a little bit more in a minute. And that's nice because then once we have things in this reliable schema, again, within the context of oncology in this case, we can enable various downstream tasks. So this is another piece of software that my colleagues have developed called Haystack. And this is a clinical trial recruitment platform. And as you can see, Haystack here is relying on structured data that's pulled out of the clinical record, of the health record. And if we don't have that information in a structured form as provided by tools like GenoLlama, then these downstream use cases aren't possible. So this is just a little bit of a wider context. Again, if you've seen the other presentations, you'll see that there's lots of work going on in this space in terms of taking unstructured notes, using the power of language models to structure them, and then having these great downstream tasks enabled. So based on this methodology, which is exhibited through GenoLlama and other projects, this is now kind of how we, in the scope of this project, reformatted our focus a little bit and what we wanted to look at. So a bit of a busy slide again, apologies, but this kind of gives you hopefully a nice overview of where we're up to and where we plan to go with GenoLlama. So what have we done so far? So I talked a little bit about how we tried to capture the great knowledge that my colleagues have around genomics in the first phase of the project, which is now complete. And we did that through schema development, bootstrap table development, and prompt development, which I'll talk about shortly. And we're now sort of most of the way through the second phase of the work that we want to do, which is then the engineering side, which myself and Joe will be leading. So this looks at, again, something I'll talk about in a moment, sample generation, fine tuning, and then finally data standardization. And then finally, and arguably most importantly, we're going to look at some evaluation. So how do we actually look at the utility of GenoLlama, which is going to be developed or is being developed to mirror this same approach as GenoLlama in terms of standardizing text to this schema. So we're going to look at trial recruitment, simulated trial recruitment as a part of evaluation, and then also this human in the loop validation, which will give us some lower level metrics about how our tool is performing. So in terms of knowledge capture, what does this look like? What were the processes that we go through to enable this pipeline that goes from our unstructured data to our schema and then enables these downstream activities? The first thing that we need to do, and again, this probably won't be new, is we develop a schema to tell the language model the exact structure that we want from this unstructured data. Again, like I say, we designed this so that it distills all this genomics knowledge in there and can be used as a point of standardization by the model. Potentially slightly differently to other approaches or other methods for doing the standardization process using large language models, we actually develop what we call a bootstrap table to go with this. So what we do is we sort of have a multi-step process where we invoke language models at multiple stages through the process. And the very first step that we do is we develop or generate these test report tables, which give us these example tests. And what this then does, as you can see here on the right-hand side of the screen, is feeds into a prompt that's going to generate some samples. We're going to generate some sample genomic reports, and then we're going to generate some corresponding, using the language model, some corresponding reports that have been structured under that sample. And having this bootstrap table allows us to kind of check all possible edge cases. So when we're doing this sample generation, we want to have a reliable mapping between input, so our raw genetic laboratory reports, genomic laboratory reports, and examples under that schema. So to do that comprehensively, we want to have this table that has lots of different examples of types of reports, so we can generate what you'll see in a moment is this kind of synthetic data. So you can see here on the side, in this knowledge capture page, stage, sorry, we develop this system prompt and we plug the schema in there, and then we have this user prompt that has this variable element to it that's also generated by a language model. So why do we do this? What are we preparing for here? Well, we take this system prompt, again, as you can see here on the left, and as I've kind of alluded to, as I've kind of said, we generate these samples. And what this sample is going to do, in this case, is generate 1,000 examples, in our initial runs, 1,000 examples of mappings between sample reports and reports structured under a schema. And that's kind of what you can see here in the middle as an example of one of these sample synthetic reports that's been output. We do all this through AWS for those who might be interested in the infrastructure that's supporting this. So we use Amazon's new Bedrock service here for inference, and specifically use Claude Sonnet to generate these samples. But of course, here we're still at synthetic data. So there's still a step to go, which is we don't want to be using the synthetic data directly. What we want to be doing with it is fine-tuning our model. So that's the next step. So what we're going to do is we're going to take these synthetic reports and we're going to run them through a fine-tuning process. So what we effectively end up with, which is a little bit meta, no pun intended, is having AI basically training AI. So that's the kind of, I would say that's the summary of the approach that we use. So we feed these synthetic reports into this fine-tuning pipeline, which again is provided by AWS through SageMaker. And we fine-tune a Llama model so that it can effectively spit out at the other end this model that can take the unstructured report and then produce the structured report at the other side. So I guess the natural question is, why don't we just use the model out of the box? If Claude is generating these samples anyway, why not? Well, I think there's a number of reasons, one of which I've already mentioned, which is we want to get this broad coverage of edge cases. There's also this intermediate step, which allows us to quality control the samples, check that the samples are representative of real laboratory reports. So then we feed this into this process and we can reliably know that we are fine-tuning our model here to give us reliable standardized outputs. So that's kind of the engineering step. And we've done so from our initial kind of fine-tuning runs, this is the sort of output that we're getting. So from one of our very, very early fine-tuning runs where we just wanted a really, really simple baseline, we took Llama 3.2, relatively low number of parameters, 3 billion, and quantized as well, so reducing some of the precision there so that we could do a quick initial training run and only 100 samples rather than 1,000. And you can see already that we're getting fairly reliable output here. There are some issues. Eagle eyes will spot this potentially, but for now, this is just a kind of early example of the kind of performance that we're getting from this methodology. Again, all backed up by this sample generation process, making sure that we're not just relying on the model's inherent training here, but actually on some fine-tuning as well. So the last step, and what I mentioned was probably the most important part, is of course evaluation. We want to be able to show that we can do something with this model. So we're sort of 80% of the way through the engineering and very, very close now to stepping through to evaluation. So kind of in the style of Haystack in terms of trial recruitment, we want to try this as well in a kind of genomics context. So what we've done is we've identified previous trials within GSTT that had some kind of genomic criteria within them. In this case, we've identified a trial called EPIC-O. So what we're going to do is we've already computationally recreated the eligibility criteria there. So what we're going to do is we're going to plug in, we're going to take this fine-tuned Llama model, and we're going to do this final step, which is data standardization within GSTT. We're going to standardize these reports, these laboratory reports from GeneWorks internally. And what we're going to do is we're going to re-simulate this trial, except do it all automatically, all data standardization automatically, all eligibility criteria checking automatically. And then what we'll get at the end is a number of simulated patients recruited, and we'll compare this to the number of actual patients recruited and get some understanding of how this fine-tuned Llama model can increase the utility in the clinical trial recruitment setting. And I mentioned as well before, another type of evaluation we're going to do, perhaps more traditional, is kind of human-in-the-loop validation. So we're going to develop some bespoke software that effectively presents the original text with the extracted text in the schema to a clinician or a genomics expert, and they can sit down and actually score how well the model is doing. And that will give us then some more standard metrics in terms of things like PPV and sensitivity that can then all feed back into refining the model and giving us a better understanding of what utility we can expect from tools of this nature. I think I'm 2 minutes early, and that is all from me, I think. Thank you very much. Very happy to take any questions. Thank you.
Martin, thanks. Now Ali asks of you, was there any specific reason for using Claude in that workflow?
Absolutely. So we found Claude was very, very good at the sample generation process. I mean, I'm probably going to start some arguments here, but I think Anthropic's models are currently leading in terms of sophistication. So at a point where we're just generating samples, we're not doing any kind of local running of the model, because obviously the Anthropic models are massive. We obviously want the best model that we can have, and we found that Claude was the best in that situation. But then, of course, it becomes much trickier, and I think even the weights are actually closed in some of the Anthropic models. If you want to actually do the standardization process itself, then you're going to need more open source models like Llama, which are still very sophisticated. So yeah, there was a conscious choice between using Claude in terms of its competency in terms of sample generation, and then switching over to Llama for more of the open source local inference that we need for standardizing the models. Hopefully that answers the question.
When, let's say, Claude has a update pushed from Anthropic, what's the quality control look like on your side of now you've got a part of your workflow that requires a revalidation? Is that, would that be true to say?
It's a great question. So yeah, obviously these models are changing all the time. So we don't have a formal process for, I mean, we have double checked the quality of the samples from the current iteration of, say, Claude Sonnet, and we're happy with the quality that it's giving us. But yeah, of course, it would be silly to ignore future iterations of the model. We don't have anything specific in place for that beyond kind of heuristic tests. But yeah, I would love to have some kind of infrastructure that, for example, took a couple of samples, automatically runs it through the latest model upon release, and can do some sort of automatic validation to say, actually, there's been a significant advance here, so let's rerun those samples. But that's very much desirable, I think. I think the baseline sample generations that we have are very sophisticated, and we're happy with in terms of the quality for fine-tuning Llama. But no, it's a great point, and this is a space that's shifting all the time, and one that we need to be aware of and plugged into, definitely. Yeah, great question. Thank you, Alex.
Thanks. Peter Ferguson asks, well, firstly, it's amazing to see and very encouraging. I wondered if you had a view on how or where this could be implemented in the NHS Genomic Medicine Service, especially thinking of how it could be implemented to support clinical trials aspirations for the NHS 10-year plan and life science sector plan.
Yeah, absolutely. I mean, I agree with all the above. Definitely want to see this kind of implemented for clinical trial, sort of getting those, like I mentioned, eligibility criteria made computational, making the recruitment process computational as well. We're actually already deploying OncoLlama, which I mentioned at the beginning, in a few trusts to standardize oncology notes to kind of enable the kind of downstream activities that we've been talking about. So once you have that standard data, obviously it's nice to have automated processes like clinical trial recruitment, but it also just sort of enables data science as well. Once you have that nicely structured data, once you have that nicely structured oncology data, it makes quote unquote basic tasks like data science on site within the trusts, I think, a lot more straightforward. So yeah, a range of application areas from, again, like I say, quote unquote basic data science through to sort of fully automating these things that traditionally been quite manual, and something that we're starting to do across various trusts around the UK is take our fine-tuned models and deploy them, OncoLlama being one of them. Another great question. Thank you very much.
And Peter, as far as I had been apprised that the priority areas here for GenoLlama's clinical trials aspirations are hemato-oncology within the host trust of Guy's and St Thomas's. So watch this space. Chandra Tiwari asks, do you mind sharing the benchmarking with the other tool for sample generation?
Yeah, so I think, sorry, if there could be more specifics, I'll interpret that question as the tool that I just mentioned. That was more of a hypothetical tool in terms of, as per Alex's comment on, if there's a new iteration of Claude, how do we check that the sample that we can't get, we aren't missing out on huge increases in quality in sample generation. That tool that I mentioned, that benchmark, is not something that exists yet. This is purely in my mind as a hypothetical thing that I'd love to have. I guess the other interpretation of that question is around the performance of OncoLlama. I'm very happy to share those metrics on performance. But yeah, I hope I'm interpreting that question. I've given two possible options there in terms of interpreting that.
Great. Karina asks, what's your experience with Gemini? Is that anywhere near the workflow or not?
Yeah, I think Gemini's just done a new batch of Flash models that we're desperate to try out. Unfortunately, we use AWS for lots of our inference, and Gemini Flash isn't currently available on AWS. So if there are people in the audience from either AWS or Google, please speak to each other so that we can try out. Yeah, because we're very excited by the Gemini models and their potential. But accessibility at the moment is a little bit of an issue. So yeah, a little plug there for others. Thank you. Great question.
Is there any plan to open source, or is GenoLlama open sourced yet or not?
I don't believe it's currently open source, but yes, I'm a massive advocate for open source. I will be pushing for this. I'm fairly sure others are of the same view. If not the weights, then definitely the pipelines will be open sourced. Yes, absolutely. Yeah, as I say, this is being rolled out to various trusts, so there'll definitely be an open source element there, definitely.
Okay. And Hannah Langoellen asked, could GenoLlama be used to convert retrospective data from genomic reports? So, stuff that's currently locked away in PDFs and whatnot into standardized data that Deborah Porter talked about at the beginning.
Yeah, it's a great question. I think there's probably a couple of challenges there in terms of, again, I don't have I'm a computer scientist rather than having a genomics background, but I believe, the further back you go, the standards change, right? So we've generated our samples based on contemporary standards. So I assume the further back you go, the less reliable that standardization process will be. Again, don't quote me on that. That's just sort of off the top of my head potential limitation. The second limitation would be if this is talking about working with PDFs, then actually, as trivial as it sounds, data extraction from PDFs can be quite trivial. So we've been sort of imagining that this is all ready to go in kind of a text-based form. But yeah, absolutely. If people have a reliable approach for extracting text from PDFs, please let me know. I know there are OCR things, but yes, I believe, again, off the top of my head, that these can be quite unreliable. So a few barriers, but yes, yeah. in theory, it could be done. It could be done retrospectively, definitely.
And Hannah, our Genomic AI Network has connections into Debbie's team, obviously, and
wonderful.
These schema are in a way meant to inform each other on what the interoperable model of genomic data sharing looks like.
Yes,
there is a
absolutely.
aspiration for this to be the retrospective counterpart to the prospective part that's going to be the unified genomic record.
Yes.
In that, populating things that are genetic tests that happened in the past.
Yeah, wonderful. Thank you.
Thank you, Martin. And
Thanks
there's
so much.
a few other ones, maybe Martin, you might be able to pick up in.
Absolutely, very happy to. Thank you very much. Great stuff. Thank you.
Thank you very much for presenting that very interesting work on really cutting edge stuff with large language models.
Thank you.
Which brings us to our last talk of the day, and that's from our very own program manager, Poppy Cohen, who will be talking you through the public-facing resources that you yourselves in the audience may want to use, and hopefully decrease the barriers to entry for the ways in which AI can be used in genomic medicine. Over to you, Poppy.
Thank you very much, Alex. So I think that a big and very important part of what we do in the Genomic AI Network team is trying to share this knowledge, some of which you've heard today, and making it accessible to all of you who are in the audience across the country and beyond. So I'm going to walk you through some of the resources that we currently have available and the next steps as well. So as you heard Alex talk about earlier, we are building a community for everyone who is interested in how AI can transform genomic medicine in the NHS and really how it can help the people, help the patients at the end of that pathway, but also help all of the dedicated staff that are working through those processes every day and reducing those pain points for people. And with that, we have a series of resources available on our website. I do recommend kind of using the website because we update that frequently. So if there are changes to these resources, that will be the kind of ground truth version that we have. You can see here on the left-hand side is the report which Nikki and Tony were discussing earlier about the public perspectives on the use of AI in genomic medicine. And this can be an important guide if any of you are considering doing a pilot or adopting a tool and thinking about what that might mean downstream for the patient. Similarly, on the right-hand side, there's a screenshot there of a kind of landscape report that Kitech did, which looks at some of the considerations amongst staff groups as well and some of the barriers that you might face if you were looking at deploying a tool. On the bottom there, you can see the screenshot of the Genomic AI tools and use case log. And this is a mix of where we know that they exist, the commercially available tools that we know of. And then also, if you scroll down in that resource, you'll find the second section, which is where we know of NHS deployments, trials that can be used as case studies. And all of those will have, where we know them, again, will have contact points as well for all of you to use. And if any of you in the audience open that resource and think, I have a fantastic tool that is not included, please do email us. Our email address will be at the end of this presentation, but also there's a contact form on our website, so you're all welcome to use that as well. At the top of that screen, which is what Peter mentioned earlier, you will see our YouTube channel. On our YouTube channel, we have the recordings of our events, so things like this, but also recordings of our monthly webinar series, which we do in collaboration with the Alan Turing Institute. They're short sessions, 45-minute lunch and learns, where we'll have a speaker come for 20 minutes and then some time for audience Q&A. Our latest speaker, which is on the screen there, was June Cheng from Alpha Genome, Google DeepMind. And our next speaker on the 28th of this month will be Hardian Health, who will talk about regulation for AI in genomic medicine as well. I also get to do the very exciting thing of launching our new resource today. So we have been creating a pathway map as a sort of AI toolkit. We've essentially wanted to make it as easy as possible. If you are someone who is working in the pathway and wants to find out where or how you could possibly use AI, we wanted everything to be in one place. So this is following from a series of stakeholder engagement sessions that we ran. And one of the things that we really heard was sometimes it's just hard to know what else is out there. And sometimes there's so much out there that you may not know what exactly is applicable to you and your team. So this is a screenshot of the kind of contents page workflow, but each stage is drawn out separately. And you can see that for every stage, we have current NHS deployments that we know about with key contacts, where they are, brief description of what the tool is, what's going on. We then have the available guidance. So that may not be produced by us, but from reputable sources, NHSE, MHRA, NICE, etc. And then the dark blue circles there are use cases identified. So that's where we've heard from people or we've seen an area where we don't yet know of an available AI tool, but that is somewhere in the pathway where there is a desire or there would be a benefit for this. So, for example, if I was a clinical geneticist in my clinic and I went to stage 1, I would see the deployment trial of ambient scribes at GOSH with some key contacts and what they did. And I would also see the NHS England guidance on the adoption of ambient scribes in the NHS. I would also see the identified use case where we recognize that something that would be really useful is an AI-assisted form filler, essentially, to do the test request forms at the end of that clinic. So that's just one example of how that could be used. But again, if you have any feedback on the tool, anything that you and your team have been working on that you would like to include, please do let us know. This is sort of for the community by the community. So if you have examples, please do send them our way. This slide is just about the next steps coming up for the network in case there is anything that anyone on this call is particularly interested in. So we are continuing the co-development of educational resources. Alex briefly mentioned earlier our next practical AI implementation workshop is the 13th of November. That is currently sold out, but there is a waitlist if anyone would like to join, and that will sort of follow a patient through a pathway, and you get to use, like literally use all of the different AI tools along that pathway, which should be a really good day. We're also continuing with our monthly Lunch and Learn series. The next one is the 28th of October, and you can find all the information for that on our LinkedIn as well. So we are also, for the pilots that you heard about today, we are doing a sort of internal evaluation of these, looking at the NICE evidence standards framework for digital health technology. And we'll be pulling that together as well, so you can see. So I hope that it will be a good example of the types of areas that you might want to consider when looking at your own AI deployments. We will also be sharing the key issues identified from our stakeholder engagements where we see fit. And with that, I would like to say a massive thank you to all of you who have attended, all of you who shared this with your colleagues, of course, all of our fantastic speakers who have joined us today. You can all join me in a virtual round of applause for everyone. I've put on there a QR code for a feedback form. Please do fill it in. It really helps us to know what you guys would like to see out of these events, because these are for you, and we want to make them as good as possible. So thank you. I'll pass over to Alex for any final remarks, but really enjoyed having you here. Thank you for attending, and thank you to our speakers.
Thanks, Poppy. It's been a pleasure, everyone. Please stay in contact through the website and our various web presences, including our webinars. I hope to see many of you at our future events, and please have this gift of time back to your afternoons. Bye-bye.